Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so this is the third and last introductory tutorial today. In this series of introductory tutorials, we heard about deep learning and about learning representations earlier this morning. Then we heard about Monte Carlo methods for approximate inference. And now we're going to hear about making optimal sequential decisions. In particular, we're going to talk about reinforcement learning. And Rich Sutton is here to talk about that. He's a professor at the University of Alberta, and he's a fellow of the AAAI. And if you're interested in reinforcement learning, then you certainly have read his book. And he's also the author of the seminal paper on temporal-difference learning, which you, of course, have also read if you're interested in reinforcement learning. All right, Rich, it's a pleasure to welcome you, and I look forward to the tutorial.
Thank you very much. It's a great pleasure to be here, but I hope you haven't all read my book, because then my tutorial will not be helpful. You would already know everything. There's a lot in reinforcement learning. It's just really exciting to see so many of you interested. And this is just going to be introduction. As I was preparing it, it kept striking me all the things that I was leaving out that I really like. But we have, as always, a limited amount of time. And so I have tried to make a selection of things that will give you a good intuitive understanding and also give you a little bit of sense of the mathematics. OK, so let's get started. What is reinforcement learning? Well, there are many phrases. Basically, it's agent-oriented learning, learning by interacting with your environment to achieve a goal. In this sense, it's more realistic and ambitious than other kinds of machine learning. It's more realistic because we're facing the problem that we don't have teachers just telling us what to do all the time. We have to figure out what to do by trying it. And it's more ambitious because we're trying to do this harder thing that's more like the real problem facing an animal or a person. So because we don't have training, we have to figure out for ourselves. We have to learn by trial and error. We get only weak evaluative training information that evaluates what we do and doesn't tell us what we should do, and it is often delayed. And this is what the phrase reward is. It's this single number that we get from the world that tells us how well we're doing and allows us to learn a way of behaving that gets us a lot of reward. So this is, as I suggested, the kind of learning that's more closely modeled after an ordinary problem that's facing an animal or a person interacting with their world. And I also like to say, and this is why it's important maybe for modern applications, is that it's a kind of learning where the system can tell for itself when it's right or wrong. Rather than having to be told, it figures it out for itself. And this enables it to be used in cases where you don't have huge data sets initially. There's a sense in which the reinforcement learning agent can create its data out of the ordinary interaction with the world. And finally, just personally, I like to think of this activity of reinforcement learning as the beginnings of a science of mind, a general understanding of goal-seeking systems and their computational properties that is separate from the sort of engineering goal of making applications that are useful, and even separate from the scientific goal of understanding animals and biological and natural systems. There's a science of mind which would be both the natural minds and artificial minds, and just minds. Okay, so that all being said, it's probably, maybe, I hope it's clear to you that reinforcement learning will touch on many different fields. It's not just machine learning, but it's psychology and neuroscience, and people talk about goals and goal-seeking systems in engineering and in economics. And so all these different fields have in common that they have to do with mentality or with goal-seeking behavior. And then we look a little bit more closely where they directly interact with reinforcement learning. We find things like optimal control. Neuroscience is a theory of the reward systems. It's very closely related to reinforcement learning algorithms. In psychology, we have classical and operant conditioning, which are very closely related. And if I was giving another talk, I would talk all about models of that are based on reinforcement learning algorithms. And of course, there's a lot of people like in operations research and engineering that do reinforcement learning ideas, and all these things overlap, and it's because they have this common goal of being realistic and ambitious about the problem that's facing a learner interacting with the world. So I just want to start by giving you some maybe silly applications, silly examples of reinforcement learning, just to get the idea across and how it's different. So as I said, it's learning by interaction with the world. So here's a little robot that's interacting with the world and learning by trial and error. And what you see here is a lot of trial and perhaps error. It's wiggling and trying many, many actions, trying to figure out which action will do best for it. And by best, you see at the tail, there's a little wheel. And that's recording its forward motion. And when it moves forward, it gets a positive reward. If it rolls backwards, it gets a negative reward. And it's trying to find a way to wiggle that will maximize that signal. It doesn't know anything about the construction of its world. It just has to try things. Okay, so after a while, it learns to behave more purposefully and, kind of biologically. But the point is, it's learned this way of behaving by interaction with the world without being told, other than being told that if it's found a way to move forward, that's good. So because of that, we can just change the sign of the reward on the wheel and thus basically ask it to move backwards. And the mechanical system is not very well designed for moving backwards, but it has found there's a way to wiggle which causes it to inch backwards. And it was able to find that without having any more information from the world, any more knowledge of the design. We've just tasked it to move backwards by making the wheel negative rather than positive. We can also take a totally different robot because there's nothing in the algorithm that's specific to the robot, and run the same algorithm, and it will also find another way to move forward with the new mechanics. Okay, so here it's found a way to move forward. The basic model, what Michael Lippmann likes to call the reinforcement learning API, is that we have two things, the agent and the environment interacting, and they just have the natural three signals passing between them. The agent generates actions, and if you were in psychology, you might call it a response, and if you're in engineering, you might call it a control signal. That goes out to the environment, and the environment returns you the state, or the stimulus, or the situation, and then also the environment returns a single scalar number, which we're going to call the reward. You could call it the cost if it was negative, the cost, or the gain, or the payoff. So notice the reward is a thin line because it's a scalar. It's just one number. Whereas, of course, the state of the world is a large complex of things, and your actions might also be high dimensional. So what's distinctive in reinforcement learning is we're going to assume that the environment may be unknown, nonlinear, stochastic, and complex. Now, in many fields, they will do each one or the other of these. So, for example, in control theory, they might assume that the world is, well, maybe none of those for classic control theory. Sometimes we assume the world is deterministic, or it's known, or simple. And here we're just not going to make any of those shortcuts. That way we are being more ambitious. Our goal, of course, is to get a lot of reward, and to do that, we learn a policy that maps states to our actions. So hopefully, from the example and from these words, you've gotten the idea of what are the signatures of reinforcement learning and the need for reinforcement learning. Number one, you have evaluative feedback from the world. You have just the reward, tells you how good what you did was, but it doesn't tell you what you should have done. You have an interaction with sequential behavior. You do some things, what you do will determine what happens next. And ultimately, it may determine substantially delayed reward. Trial and error. Trial and error involves the need to this dilemma between exploration and exploitation. You both have to try a lot of things to find out what's the best thing, but you also have to do the best thing so that there's some point to all of your learning. The world, these examples maybe are not so obvious, but because of the way our algorithms work, we end up intrinsically having to do with non-stationary learning algorithms. And finally, and this is more conceptual, we have, in reinforcement learning, we're much more often dealing and recognizing the fleeting nature of our time and of data, so that we can't often like make super many processes over the same data points because, well, they come past us and later we'll be busy doing something else. So it's not really that useful to save everything and process it later. That was the wrong key. That was the wrong key too. That was the wrong key too. Okay. So I wanted to just start by briefly mentioning some of the things that have worked out well. So one of the oldest ones is a reinforcement learning method was used to learn to play backgammon better than any backgammon player before and better than any person. So let me just briefly tell you about that. This was by Jerry Tesaro. It's called TD Gammon. And backgammon is this major game that rich people play. Anyway, it's actually a full game, quite complex. It's stochastic. And so he mapped the state. The state is all these pieces. And that was mapped into the input to a neural network. This was in the early 90s. And that neural network, through its hidden, just one hidden layer, so maybe it's not deep, and eventually produced an estimated value of the board, which is roughly the probability of winning. And it was a good accomplishment because he started with a random network, and then he just played many, many games of the system against itself. Now, how would you play a game? To play a game, you have to evaluate, you have to be able to pick moves. And so he used a shallow search with this thing as the evaluation function. So he just looked ahead like 2 or 3 ply and applied this value function at the terminal nodes, and then backed it up to pick the best first move. Okay? And so in this way, you could play lots of games against yourself. You play lots of games against yourself, you have experience, and you can do what's called temporal-difference learning and improve the value function over time. So you learn as the value function gets better and better. After 6 weeks, playing in the corner, it comes out and it's the best player backgammon that the world has ever seen, including beating all the human experts. Now, the original version of the system used handcrafted features, and later it was repeated, though, with raw board positions. So it was actually a nice example in today's context of doing well with very little prior knowledge. Okay, just quickly, another famous example is learning to fly helicopters automatically. Another example of wide use of reinforcement learning is in things on the web to place and select advertisements and articles. And it's been used, you've all heard, I think, of Watson's, of the Watson system, IBM's Watson system, that learned to play, though that didn't learn to play Jeopardy, it played Jeopardy, it did very, very well, beat the best humans, and part of that, the strategic part of it, some of those decisions were made by reinforcement learning. I'm sure many of you have heard about the success on Atari games by Google DeepMind. Let me tell you, just show a little bit about that. Okay, I think I'm going to start with the behavior. So here we have playing Atari games automatically by a combination of reinforcement learning and deep learning. And you see, we have 3 different systems, 3 different games that are fairly different, but the exact same learning system was used on all the games. So it actually learned to play 49 different games. So where did these games come from? These games came from Alberta, from Michael Bowling, my colleague at Alberta. He designed the Atari learning environment, or he created it, made it into a learning environment for machine learning. And the guys at DeepMind picked it up and made this amazing agent, this deep Q network that learned to play them all from self-play and from the score alone. And one of the impressive things is it really mapped raw pixel images as the input and produced prediction of the final score. What I'll show you is called an action value. And in this way, it learned to play very well, not really superhuman level in most cases, but better than all previous algorithms and at or near a human level for more than half the games. Just note that this was the same learning algorithm applied to all 49 games. There was no tuning to the particular game. That perhaps is what's most impressive about it. Okay, returning to my list, I just want to say that in all these cases, performance was or is obtained that's better than by any other method and was obtained without human instruction. Okay, so what I want to try to cover today, I finished the introduction. Now I'm going to get into it. You guys got to start really paying attention now, because I'm going to, and the way I'm going to, what I would hope to cover is first, what's the problem, and then then we'll turn to the solution strategies, and we'll do first exact methods, which means table lookup methods, the methods that maybe don't scale all that well, and then we will add function approximation and look at a variety of methods. Okay, so I want to start by doing something a little bit interactive. I don't know if we can be really interactive in such a large room, but maybe some of you guys in the front could like commit to participate. It'll be easy. Let me see if I can get this to work. Okay, here's my Lisp program that's going to be a Markov decision process. I mean, I could give you the definitions, but I thought you should experience it first, as if you were an agent interacting with the world, which, you know, you are. So, let's go. Here you are. You're facing your world. I'm going to tell you a hint. You've got two actions. You can do action number 1 or action number 2. And I'm going to ask you what action you'd like to try. But I will tell you some things that you're now at time 0, you're in state A. Okay, what action would you like to try? 1. Good. 1. You get a reward of +10. Life is good. What action would you like to do next? Because you don't know if +10 is a lot or if it's a little bit. It's evaluative. It evaluates how well you did. It doesn't tell you what you should have done. 2. Minus 14. So what would you like to do now? Look, there's two things. You have to pay attention to two things. You want to explore, right? Try things, find out if 2 is really good or not. But you know, you have to exploit as well, because the name of the game is to get reward. When you get that minus 14, you have to feel bad. I think rationally, since you've tried them both once, you have to try 1 again. Aren't you glad? You're feeling it. Good. Good. Okay. Now, okay. So I'll say some things, because you don't know what my Lisp program is doing. Okay, but it's a Lisp program. It's not changing. It's not paying attention to, like, you tried 2 things in a row and it's going to do a bad thing next. It's not doing anything like that. The reward you get will solely depend on your action and, of course, on the state. The great thing about this demo here today is you're all saying different things, and I can just pick whichever one I want. Let's try to. Oops. My hands aren't really that good. Let's see if I can go back. Good. Okay. Let's try the other action. Just one more time. Okay? You guys really want to do 2? All right. Even though it's bad, we'll do your 2. It's better. Okay, now you guys, whatever you want to do. 1, I heard 1. 1. 1 is the loudest. I don't know. So ask yourself, what's going on in your head? Okay? What are you doing to try to figure this out? Because this is the best way to make a learning algorithm, is to pretend you are in the chair of the learning algorithm, and what are you going to do? How are you going to learn? What are you going to remember? Like, a lot of the data has scrolled off the screen and you don't even remember it anymore, you know? That's what I mean by the fleeting nature of time and data, online data. Okay, so has anyone figured out the optimal policy yet? If you're not sure, well, let's just try some more things. Figure it out. What should we try? I heard 1 first. You have to be quick. Okay, I heard 2. 1, there's a big 1. Anil, everybody, raise your hands. 2 is the winner. 1 is loud. 2. 1. 2. 1. Okay, is this better? Why is it better? We're doing 2, and then we're getting into B, we're doing 1, and then we're doing 2, and we're getting into B, we're doing 1. Why is that better? Better than what? Like, how good is this? This feels good. We got those 38 and the 42, and then we got the minus 10. Gosh, how do we even say what's better? Well, we want to get a lot of reward in the long run, okay? So, I don't know, if you look at this strategy here, we're getting like a plus 40 and a minus 10 alternately. And so that's how much per step? Minus 10, plus 40, plus 30 in 2 steps. So it's 15 per step, okay? And if we go back to the other thing that we were trying, which was just all 1s all the time, that gets like, it's random, it's stochastic, but it's about 10 each time, okay? So, I don't know, that's we can, okay, what did we learn from all this? Let's go back to our slides. Okay, so maybe you can, this actually is the true model of the world. I'm sure you didn't compute this. I'm not sure we saw all these transitions. But maybe, I think we did work out the optimal policy. The optimal policy is shown here. So we have the 2 states, A and B. And we learned that in A we should do 2, and in B we should do 1. And that one got us 15 per step, got us a lot of reward anyway. And here's the world. The world has got 2 states. And from each state, we have 2 actions, action 1 and action 2. And as we said, the right action from A is to 2, and the right action from B is to do 1. Now, the world is stochastic. It's stochastic because the rewards are stochastic, which we definitely saw. But there's also some other stochasticity that we didn't see. For example, if we did 2 from A, we usually went to B, and I think that's the only transition we saw. But 1 time out of 5, it actually will go back to A. And that's true for both of the actions from B. They also have 1 chance in 5 of going back. So anyway, I hope you learned about learning a policy by trial and error and experience. So let's now try to make it formal. Okay, let's think of this as our example. Okay, so we're going to have discrete time, right? 1, 2, 3. We're taking things successively. We're going to have states in each time step, and we're going to have an action in each time step. And let's just make these finite sets. Like, these are quite small, but finite sets, they could be quite large. Like in backgammon, the number of states is enormous, like the number of particles in the universe, even though it's still finite. And actually, let me comment on that, the finiteness. These are finite MDPs, and that's just fine. The fact they don't need to be infinite to be hard, right? And in fact, I think it's a mistake to jump too early to considering the infinite state case or the infinite action case, because it just makes the math more confusing. And I'm really in favor of keeping simple math. So one example of that is I'm even going to assume that the set of possible rewards is finite. The rewards really could be any real number. But if I say they're finite, I can do things like here at the bottom. I have a probability of, if you're in a state and an action, what's the probability that the next state will be something and the next reward will be something? I can talk about the probability. If I had continuous rewards, I'd have to talk about the density function or something like that, and that just would make me confused. So let's just talk about ordinary probabilities. We can use sums. We don't have to use integrals. I really don't like unnecessarily fancy math. Okay, so, but I think maybe the most important line here is this one. Life is a trajectory. Life is a sequence. States, actions, rewards, next states, next action. Then it just goes on forever. And these are the real events that are happening in our life. So I'm going to use the statistician's convention that the real events, the random events, are capital letters. Okay? Capital S of t means whatever state happened at time t. Okay? Whereas I'll use lowercase letters for sort of the instances. So I can talk in general about the probability that this random reward has that value and the next state has that value, given that the initial state has this value and the initial action has that action. Okay? And so what we mean by Markov is that the world is stochastic in this sense, and it's state dependent, state and action dependent. Okay, so I hope that's clear. If you really had a clarification question, I wouldn't mind if you raised your hand, although for the most part, we're going to find it's best to save most of the questions for the end. Okay, so that's the world, or the environment. Now let's talk about the agent a little bit. So the agent is searching for a policy. So often we'll talk about deterministic policies. So those are just functions from states to actions, like shown here. And then the actual, we can generate an agent because we're applying our function, our policy, to the state we're in to generate the action that we're in. So we've already seen a policy. This is a policy. It was our optimal policy where our little test problem. So we mapped states to actions, states to actions. Now informally, our goal is to choose our actions so as to maximize something, and we hadn't fully decided what it was we were trying to maximize. It was something about the future rewards and maybe the sum of them, and there are actually several possibilities here. But we're going to consider just the simplest and most straightforward one, which is that we choose each action to maximize the discounted sum of the future rewards. So like the first reward is going to full value, and the second one is going to be discounted by gamma. Gamma is a number less than 1, like 0.9. Okay, and then for each successive reward is discounted by another factor of gamma. And then we can just sum all of them up to the infinity, and because there's the discounting, that sum will still be finite. It'll just be a number. And that's what we're going to be interested in. Okay, so we're searching for a policy. So let's just think a little bit how hard it is to find a policy. Like, how many policies are there? Well, there's actually an enormous number of policies. So the number of policies, even just deterministic policies, as opposed to random policies, it's exponential in the number of states. It's actually the number of actions carried to the power of the number of states. So if you have large numbers of states, and we do in our applications, there are going to be an enormous number of policies, and it's really quite challenging to search that space to find the best policy. So our major theoretical trick, to deal with this huge space is we're going to call action value functions. Action value function is a way of giving values to state action pairs. Okay, it's a way of saying how good it is to be in a state, take an action, and thereafter follow a policy. So we should look at this equation for a little bit. So Q pi SA, the value of being in state S, doing action A, and thereafter following pi. Okay, so the value is the expectation of that thing we were just looking at, the sum of the rewards discounted. That's what we're interested in. And then, but it's conditional on, so the sum of future rewards after t, so it's conditional that we start at time t in the indicated state S. Right? That matches this S. And the action we take is the first action is A. Okay, and then ever after that action at time t, the subsequent actions from t plus 1 all the way out to infinity have to be selected according to pi, however pi says. Okay, so that's the game. And it's important to note that this action might be one that pi would never select. Okay, so here's our example, and our optimal policy was to go this way. But we could talk about, what if I was at A, what's the value of taking this other action, action 1 in state A, and later follow the optimal policy. So what if I went here and then started following optimally ever after? Okay, that would be this number, 130.39. If I worked it out correctly, the night before last, actually it was a little hard to work it out, but our programs figure it out in general. And so for each one of these choices, each state and each action, we're going to get a number that says how good it is to be in that state and do that action, and thereafter follow the optimal policy. Well, this is an arbitrary policy, not necessarily optimal. In this case, we have the optimal policy, and these numbers are for that optimal policy. They're also for the discount, a choice of the discount rate, 0.9. Okay, so we can give state action pairs in the context of a policy a number, and we can use that. So how can we use that? Well, now I'm ready to define what we mean for a policy to be optimal. So a policy is optimal, and we're going to call it pi star because it's the best policy, if it maximizes the action value function. So we think of the action value function as something that, well, the policy is like an argument to it. And we can talk about how do we get the highest values as a function of that argument. Okay, so the max over all possible policies, that huge, enormously large space, such that there's no way we could search it, and there's no way we could run this max, because that's a huge space of policies. But if we do take the max over all that whole space, what's the very best we can get in a state action pair, and the best policy? That would be the value. That tells us whether pi star is optimal or not. Now, this comes up often, so we're going to give a special name for it. The value function for pi star, we're just going to call it the value function star, the optimal value function. Taking the best over all possible policies. Okay, so now, if we had such a thing, if we had the optimal value function, it would be easy. Our life would be easy to behave optimally. And this is what we would do. We will just take the argmax, or we will, as I say, greedify our value function. Okay, so argmax. And that always confuses some of my students, so let me explain it, make it clear to you, even though you're much more mathematically experienced. Let me just say what it means in an intuitive fashion. Like if you were to take, you're maxing like, instead of values, like the height of people in a room. All the people in this room, take the max over them all. The max would just be, how tall they were. Maybe they'd be 7 feet tall. Okay, so the answer would be 7 feet. Whereas argmax would be the person. It would be, Joe. Joe is 7 feet tall. Okay, so here we don't want the number, or the biggest number you can get from the value function. We want the identity of the action that achieves that maximum. Okay, so this is called greedification. We have our value function. We basically convert our value function to the policy by greedifying it, seeing, I'm sitting here, I've got all these in one state, and I have all the actions available to me, and I just see how valuable each one is, and then whichever one is most valuable, I say, I will do that one. Okay? That will be guaranteed to be the optimal policy. So whatever delayed consequences there are of that action, they have all, somehow, all been brought forward into a greedy, immediate choice. It's Q star is doing this for us. It's saying whatever delayed consequences there are of doing this action, I'm going to tell you how good it is right now. Q star brings that delayed consequences into the present, the future into the present, and allows you to act optimally with very little computation. You just have to take a max over the actions. The action set is often very small, and certainly is much larger than the state space or the policy space. Okay, so the words we're going to use is greedy. This is a greedy action selection, and it follows that there's always at least one optimal policy that is deterministic. So now we're ready, because we've formulated the problem, and so we can talk about solution methods. And let's talk about the exact solution methods, or tabular methods, because this will enable us to finish introducing most of the ideas. Okay, and it's very tempting to do Q-learning at this point, and I'm going to give in to that temptation. It's very tempting because it's so simple, and having specified the problem, I can now give you the algorithm. I can give you an algorithm that you could go home today and code without knowing anything more about the theory. Okay, so here's the algorithm. You're going to make an array. The array, we're going to call it Q, capital Q, because it's going to be a random variable we're going to learn. We're going to learn it. And it's going to come to approximate what? Q star. Okay? So we initialize it arbitrary. Like if we were smart, we might initialize it in a good way, taking advantage of our prior knowledge to be an approximation to the correct action value, or we could just make it all zeros, or fill it up with random stuff. It doesn't matter. Then we're going to choose actions, and we're allowed also great flexibility here. We could choose actions in any way. We might choose them based on our estimate Q. Okay, but how we choose them, we're going to have to choose. We're going to have to try all the actions in all the states, and in fact, because the world is stochastic, really you have to try everything in every state an infinite number of times if you want to find the optimal behavior. Okay, so step 3 is the magic step. It's really just one line of code. Is that for each time step, we're going to change one element of the array. We're going to update the element of the array for the state that we just passed out of. Okay, so we're going to go from time t to time t plus 1. We're going to change the element of the array for time t, for the state and the action at time t. And we're going to increment it by step size times an error measure. Okay, the error measure is the difference between our original estimate and this thing. This thing is like a target. This thing is the first reward, and then look at the next state we're in, take the best action according to our estimates at that state. Okay, how good is the best action according to our estimates at the new state? And we're going to reward ourselves, or we're going to feel good about our outcome if the reward plus the discounted version of what we expect at the next state is bigger than what we were expecting for this state. Okay, and we'll be disappointed if it's less. And based on that, we will update our estimate. We'll change our estimate up or down. Okay, so that's the whole algorithm. Well, no, there's one last step. Is if you want to really converge to something, you have to reduce your step size parameter, and so you have to do that in there's several possible ways. And then the theorem is that if you do that appropriately, then your estimate converges to Q star, and once you have Q star, then you can do the greedy thing and have an optimal policy pi star. And so this is kind of amazing because we've found a way to learn long-term optimal behavior without a model, just by interacting with the world and trying things, figuring it out as we go. This is for an arbitrary Markov decision process. Markov decision processes are a very general framework. They're completely nonlinear because they're like a table of possible transition probabilities. And so it's a very, very general case. Okay. Let's have a demo. Right. Okay. Now this is going to be an exciting part of the talk because I realized my demo, just like 3 minutes before the talk started, I realized it was broken. But let's see if we can do it. Okay, not that one. Hopefully it's this one. Okay, so the thing that's broken, this is my grid world. This is like a maze, the little agent there. This agent moves around up, down, right, and left. It starts here, and then hopefully it gets to the goal where it will get reward. And I just have to say, I think I'm sort of known in the field because I like grid worlds. Okay, and yet I started this whole talk by saying reinforcement learning is about being more realistic and ambitious. And I can't really say the grid worlds directly meet those criteria, but yet they do in some sense because no one tells you what to do. They involve, you still need trial and error. You still have great unknown worlds to explore and find out. And the world can be, well, it's not stochastic, but it could be stochastic. And I guess the important thing is that we have rewards. And so I really would claim that grid worlds are in certain ways, certain controlled ways, more realistic and ambitious. Okay, anyway, I was telling you why this thing breaks. So this thing broke for me because the demo is all prepared. All I have to do is say go. Okay? But the resolution of the monitors and everything are such that the button that I press to say go is down here. Okay, and I've got no way to press it. It's all ready to go. If I could just catch a corner of the button, it would be good, but I can't. I've tried it. So what I'm going to do now is I'm going to unplug my computer from the monitor. Everything will go black, and then it will revert to normal resolution. I will press go, and then I'll plug it back in. And I've only tried this once, and it worked. 3 minutes before the talk, or really like 1 minute. Maybe you saw me. Okay, so I'm going to try that. Here it goes. There's go. Come on, plug in. Okay. Okay. Okay, we're going. Okay, so we're trial and error. We're moving around randomly. So what's the reward? The reward is +1 if you get to the goal. Okay, otherwise it's 0. And it's moving, so we're doing Q-learning, but we're behaving totally randomly. Random action. So this is sort of, this is showing the fact that the policy, the action selection method, doesn't have to respect the action values, the learned values. So we are behaving totally at random. So even after it's learned the good policy, it will not follow it. Okay? So right now it's learning a good policy. The arrows indicate which way it thinks are best. Actually, the four lines are the 4 action values. And this is, the arrowhead is on the action value that has largest value. Okay, and then the green is like proportional to the height of the largest action value. Okay, so you understand everything here. You understand how these things are being learned. And by this point, they're almost all right. This one's, oh, that one's right. This one's not right. It hasn't learned the value of going right here, or left here, or up here. Oh, just got those two. And you see, it's moving around randomly. It's not behaving well at all, because it's just behaving randomly. When it gets to the goal, it's automatically transported to the start. But it needs to behave somewhat randomly in order to explore. And so this is the feature or bug, it's your choice, of what's called an off-policy method. It's learning about the optimal policy. And what you see here with the arrows is in fact the optimal policy. It does the correct arrowhead. The arrowhead is on the correct action in every case. So it has learned the right thing to do, but it's just not doing it. Okay? It's behaving randomly. So there's 2 policies involved. One is the policy that it's using for behavior, and one is the policy that's learning about. We call it the target policy. Okay, so the target policy is the optimal policy, and you see it's brilliantly learning the optimal policy. Okay, so we have 2 policies, and when you have 2 policies, I don't know, we call it off-policy learning, because you're learning off the policy that you're following. Yeah, so you're learning off the policy that's generating the data. Anyway, oh, can I stop this? Let's just try hitting this button. Maybe my whole computer will crash. I'm going to try it. Okay. Whew. Okay, so that was the off-policy demonstration. So I'm trying to build up, I've given away the punchline, I've given you Q-learning, but now I'm trying to build up some of the theory behind it, sort of explain how it works and how we can generalize it to harder cases. Okay? Key element of our theory is what's called the policy improvement theorem. And so we've already talked about the action value function. So suppose we have the action value function for some policy, any policy. So that means, we know this thing. Suppose somehow we were able to know it. Then we can do the greedification trick to make a new policy, pi prime, that is guaranteed to be better than pi. It's not going to be optimal, okay? That's going to be better than pi. And we just, by greedifying, we do the argmax over our thing that we have to get pi prime. Okay, and you should note it's not unique because argmaxes are not unique. Like there could be 2 people in the room that are 7 feet tall. Okay, and I could give you Joe or I could give you Mary, and they would both be possible argmaxes. Okay, and so there could be 2 actions. And this happens a lot, like in the grid worlds. You want to get to the corner, but you can either go over and then up, or you can go up and then over. Right? Argmax, non-unique. Okay, but what do we mean by better? We've talked about optimal, but let's tell them what we mean by better. So one policy is better than another one if for all state action pairs, it has a higher value. Okay? That's all we mean. Now, it's greater than or equal to, actually, but what if we do get equal at all pairs? Well, then we know that both policies are optimal. Okay, so if you think about this, this kind of gives us a strategy for proceeding. Okay, that strategy is called, well, I like to call it the dance of policy and value, because it's more, I don't know, mythological or romantic. But the common name in the literature is called policy iteration. You could call it either one. I'm going to call it the dance of policy and value. So we have some policy, and we can evaluate it. Suppose we could evaluate it. Let's not worry yet how we're going to do, but I'll show you in a minute how we can form it, go from a policy to its value function, at least approximately. And then you can greedify it, and you know, by the improvement theorem, this pi 2 has to be better than pi 1. And then we keep going. Okay, we got pi 2, let's evaluate that. Q pi 2, we'll greedify that, we'll get pi 3. Pi 3 is better than pi 2 and better than pi 1. We just keep going. And then eventually, we're guaranteed that we will get to pi star. And of course, when we evaluate pi star, we'll get q star. And then if we greedify q star, we'll get pi star again, so we're done. Okay? So the guarantee is that each policy is strictly better than the previous until the time comes when they're both optimal. And there's no way you can get stuck in a local optima because we're using tables and arrays and exact computations. We're not doing neural networks or some kind of function approximator. But it's important that if you did have this case, that there are no local optima, you will find the optimal policy. Now, moreover, you usually converge in a finite number of steps. Well, no, there's a theorem that you converge in a finite number of steps, and you can actually see that yourself because each policy is either better than the one before it, or it's optimal. So, and there's only a finite number of policies. So as you go through here, eventually you have to hit the optimal one. Now, we also discussed earlier how the space of policies is enormous. So it's not too much of a safety blanket, of a guarantee. But in fact, it usually converges in very few iterations. In practice, it converges in very few iterations. So it's actually a very happy fact and a very good strategy for finding the optimal policy. Okay, and I want to say some more about it. One is that it's very robust. It doesn't matter how you start out. It doesn't matter how you do the updates. You can delay them, do it asynchronously with distributed computers. Or you don't have to really fully evaluate a policy, and you don't really have to fully greedify it. Like you might only make some of its states more accurately valued than others. And then you could only greedify some states, or maybe just look at two of the actions and make, throw away the worst of two possible actions, even at a single state. So there's always a bunch of ways in which you can do it incompletely and partially. And it doesn't matter. As long as you keep going, eventually, even if things are stochastic and you throw noise in, it's good. It works very robustly. And in particular, it works if we only have a single state updated at a time, and we do it by a random amount that's only correct in expectation. So that's what happens with our learning algorithms. It's what's happening in Q-learning. We're moving in expectation in the right direction. Okay. But before I can quite do the final step, we have to talk again about the exploration-exploitation dilemma. We know, because we did the early example, that you can't do the action that you think is best all the time because you might miss out big and forever on a better action. And so you have to try them all many, many times. But you also can't explore all the time because then you never get any advantage of your learning, like in that poor grid world system that kept being randomly, even though it worked out the optimal policy. So we have to both explore and exploit, but neither completely. And maybe we need to find a right balance. That's an interesting open problem in the field. I don't think we really have deep insights about it yet. But let's start just by reminding ourselves how we handled this dilemma for Q-learning. Does anyone remember how we escaped the dilemma? Well, the dilemma, I guess, well, in the grid world, we just explore it all the time. That's not the best way. What we did in Q-learning was we had step 2. I don't know if that shows up. It shows up a little bit. Step 2, we said choose actions in any way you wanted, perhaps depending on Q, but such that you do everything infinitely often. So we kind of finessed the problem. We said, oh, it's outside the learning algorithm. Someone else has to arrange that we get the appropriate data. We have to try everything in all states. Okay, last idea, bootstrapping. Key idea of reinforcement learning. It underlies both dynamic programming and all temporal difference learning methods. Q-learning is a temporal difference learning method. So this idea is that of bootstrapping one estimate from another estimate, updating an estimate from another estimate, a guess from a guess. And the theoretical idea that's based on is called the Bellman equation. So there's 2 Bellman equations. Let's do them one at a time. Okay, the first one is the Bellman equation for Q pi. Now this first line here is exactly the one you've seen before. It's just the definition of Q pi. Okay, it's the sum of all the future rewards appropriately discounted, given that you're in a state, do an action, and afterwards behave according to the policy. So we just note that this can be rewritten. We take the first reward, that just carries down, but all these have a similar form to the original. They're like the original, but delayed by 1 step and then discounted by 1 more factor of gamma. They have a recursive relationship. So substituting for all the future ones, we can actually say the action value of the next state action pair. Okay? And now we don't even have to be conditional on all the future. We just have to say, well, the first state has to be as specified, and then the very next action has to be according to pi. It doesn't really matter what happens after that, because all the summary of what happens after t plus 1 has been incorporated into our action value function. Okay, so this is the Bellman equation. It's just true about Q pi, but it might be a good basis for an algorithm. Okay, now I said it's the Bellman equation, but there's 2 of them. This is for expectations, and then this one is for optimality. So this is for Q pi, for any pi. This is going to be for pi star, for the optimal policy. Okay, so the optimal action value function has a Bellman equation. It's kind of similar, but here, when we look at the next state, s of t plus 1, instead we consider all the actions and we take the best of them. Okay, so this case is really nice because I haven't even had to condition on the next action, right? Because the next action will be just maxed over it. And so there's no conditioning other than the state I'm in, the action I did, and then the rest just comes right away. Now you've also may recognize this thing, because this is what we're using in Q-learning. This is the target. We're saying, we had some estimate, and then we will look, well, the target, in Q-learning, we're using Q instead of Q star, okay? But it's the same idea, and that's the way Q-learning works. It's really implementing the Bellman equation, which is an expectation thing, by sampling it on every time step. Okay, some other remarks about Q-learning. As I said, it's off-policy learning. Off-policy learning, let me just tell you the definition again. It's learning about the value of a policy other than the policy being used to generate the trajectory. And this is what Q-learning does, because Q-learning is learning about the value of the deterministic greedy policy, which gradually becomes the optimal policy, from data while behaving in a more exploratory manner. It's off-policy learning, and that's essential to its strategy. Okay, so maybe I've said this terminology. Target policy, behavior policy. Target policy is the target of your learning. Behavior policy is generating your behavior. If these 2 happen to be the same, then you have on-policy learning, and we'll be talking a lot about that when it comes to function approximation. And that's where we're going next. It's always a surprise to me. I always prepared this talk, using the presenter mode on my computer where I can see what's coming up. But with all this setup, I can't do that. So I'm always a little bit surprised when I find out where I am. We're at the beginning of part 2, where you do function approximation. And remember why we need function approximation, because yeah, we can do with Q-learning and things like that, we can find optimal policies for arbitrary worlds, but only if everything can be represented in arrays in our computer. Okay, and very quickly the real world becomes too complex, too many states, too many state action pairs, and we can't represent it. And even if we could, we wouldn't want to, because it would be too slow to fill all that up. You need to generalize from your experience to new cases in order to learn quickly in a reasonable amount of time. And so we have to ask, will our methods work with approximations? In particular, will they work with the notion of a function approximator? Function approximator, the obvious way, there are several ways to use function approximation in reinforcement learning. You could learn it to approximate the policy, you could learn it to approximate a model of the world, but the first and most important way is where we use the approximator to approximate the action value function. Okay, so yeah, I thought I found all the bugs in my slides, but right here, this thing Q should have a hat on it, right? Because this is going to be our approximate. So, all in the future, so we're going to learn an approximate action value function given a state action and a parameter, theta. It's going to be called Q hat from now on. And we will use it to approximate Q star, perhaps, and we'll also sometimes use it to approximate Q pi, where these two could be different, and it's really sort of the difference between on-policy learning and off-policy learning. Okay, anyway, we're going to use an approximator, Q hat, which uses a parameter. Like those parameters might be the weights of a deep neural network. Okay, or more often in my own work, the approximation is a linear approximation. So we have a bunch of features, we take the inner product with the parameter vector. Okay, so then we have simply a linear weighting of features, and I still think this is where we should be working for a while longer until we solve the theoretical problems. Of course, we should also do deep networks and everything else, but the linear case is not solved. Okay, now I just want to say it's a powerful concept. For example, if you have parametric representation, you have essentially the problem of hidden state, because your features may not tell you all about the state. And so subsumed in the problem of a function approximation is the problem of hidden state. And I like that because I used to have two problems. One was function approximation, one was hidden state, and now I only have one problem, function approximation. Another comment is that we want, if we really want to scale to large problems, our computation has to scale linearly with the number of parameters. Okay, this is what a deep network does, but many systems that are considered in theory will assume you can have the computation the square of the number of parameters, and we're going to try to avoid that. So does Q-learning work with function approximation? And the answer is yes. It works, sort of. I mean, actually it does work. It works pretty well, but it sort of isn't guaranteed to work. So there are counterexamples, simple examples where you run Q-learning with function approximation. I'll show you the equation, the idea, on the next slide. But even for the linear case, we have counterexamples. And so we're not doing something right. There's something wrong. Maybe there's several things wrong. There's some things we don't understand. And this is going to be my bottom line about function approximation and reinforcement learning, that there's a lot of basic questions that still remain open. Sure, we can make things work. We do have theorems and guaranteed convergence properties, but for many cases, like Q-learning, we don't have a good theoretical understanding. Now this is true even though we talked about the Atari games and the deep Q network. Well, that system, at least some versions of it, are using a Q-learning, a variation of Q-learning. And so they've found other ways to get around the problems. Or they didn't worry that there was a small chance that their system could fail, could diverge, and the weights go to infinity because, well, if that happened, they would just throw that one out and try again. Okay, so Q-learning, how do you combine it with function approximation? Well, consider the following objective. This is an objective based on the Bellman optimality equation. We're basically comparing this thing, which is the target of Q-learning, except where we substituted our approximation, Q hat, for the table. Okay, so if this was just plain Q star, then this would always be 0. There's 0 in expectation. So we just take this thing that we want to be 0 and we make it into an objective function, make it into an error, compare our guess with the target and square it, and then take the expectation. That's a loss function. So notice that the target depends on the parameter, depends on theta. And we have to ignore that, okay? We ignore that dependence because this is viewed as a target. We don't want to say, I'm going to change my guess to equal, well, we do want to say I change my guess to make it more like the target, but we don't want to say I'm going to change my target to make it more like my guess, okay? That's intuitively why it's not a good idea, but in fact, it's not a good idea. People have tried it. If we had more time, we would go through more elementary examples and show you why it's not a good idea. So it's not what almost anyone ever does. So we ignore that, and we get our update. So our update, in some sense, it looks like Q-learning. We're going to change, I guess I need to go through this carefully. We're going to change now not a table entry, but we're going to change the whole parameter vector on each time step. Okay, so the change in theta at each time step is going to be step size times an error. And this error is very much like the Q-learning error. We've just substituted the array, capital Q, with the estimated function approximation, Q hat. Otherwise, it's the same. And then by gradient, because we're doing a gradient approach, we've taken the derivative, and we need to know how the parameter vector theta will affect our approximation. And the fact that we're ignoring this effect shows up here. We're only saying, how would theta affect Q hat at the starting state? And based on that and the error, we're going to do our update. Okay, that's our update. Semi-gradient Q-learning. Now, I've told you this algorithm doesn't really have good theoretical properties, and so let's kind of lay it aside and look at an algorithm that does have better theoretical properties. And it's very similar, and I've sort of written its slide to look very similar. So here's the slide, a similar slide for an off policy. Actually, the Q-learning is off policy. I'm going to give you now the on policy algorithm. The on policy algorithm is called SARSA. Okay, so here's SARSA. And our objective function is based on the Bellman expectation equation instead of the Bellman optimality equation. This we saw earlier. So our target now doesn't have a max in it. Instead, we take whatever action it is we do on the next step rather than maxing over possible actions. And that's going to make this into an on-policy algorithm. Okay, but otherwise, we do the same thing. We ignore the dependence of the loss on the target, on theta, and just take the derivative with respect to the second part. Okay, so this gives us our algorithm, and it's the same as before, except instead, let me just flash that one back. Here we were taking the max, and now we're just taking whatever action we do at time t plus 1. Okay, that makes it an on-policy algorithm, and it's going to approximate q pi. It's not going to approximate q star. Because of this, we should arrange for pi to be near greedy. So that way, we'll be approximating something that's close to the optimal policy. Near greedy. So the word we're going to use is epsilon greedy. Let me explain a couple of these things. First, why is it called SARSA? Well, it's the only learning update that uses exactly 5 things from the trajectory. The state, the action, the next reward, the next state, and the next action. So if you just kind of step back and read that, it says SARSA. Okay, so that's why it's called SARSA. It's just really the same thing as the TD0 algorithm applied to state-action pairs rather than to states. Also, what is an epsilon greedy policy? Well, an epsilon greedy policy, it's a stochastic policy. It's not deterministic. We've only explained deterministic ones, but I think you can just imagine what a stochastic policy is. Instead of always picking one action, you pick actions with different probabilities. And so usually, we're going to take the greedy action, but with some small probability epsilon, we'll do something at random. Okay, and that's epsilon greedy. So typically, you want to pick epsilon small, maybe a 10th, or if you want really good behavior, you might take it a 100th. But that'll slow down your learning because you'll do less exploration. So epsilon greedy, this is one of the common, trivial, hacky ways to get exploration because we're forcing ourselves to behave at random, and so we will explore. On-policy methods have much better convergence properties. We don't have the problems of Q-learning. We have these guarantees. So in the linear case, we have guaranteed convergence for the prediction case. Prediction means we have a fixed target policy, we just want to know what its value function is. The control case is when we want to not just know the value of a given policy, but we want to find the best policy. So in the control case, we're trying to find Q star. In the prediction case, we're trying to find Q pi for a given pi. Now, it's a little complicated. I didn't say it's convergent for the control case because it isn't convergent. It actually continues to move around for the control case. We never settle on a single parameter value, but it moves around within a bounded region of a good policy and a good parameter. So this is what we mean by chattering, is that it never ever settles. It just keeps moving around, but it's close to the answer. Maybe it's an interesting theoretical problem, or maybe it's something we want to get rid of. We have ways of stepping around it. Let me just say, the chattering tends to come about because the action values, if they involve a max. Remember, greedification involves a max. So if you have two actions that have almost the same value, and you learn a little bit, one steps above the other one, the policy switches dramatically, even for a small parameter change. And so that causes chattering. So now if we turn to the nonlinear case, of course, that's what we do in deep learning. We have nonlinear function approximators. And for this case, things are also, I would say, well behaved. But there is a counterexample. It's an artificial and contrived counterexample. I'm not really concerned about it. But our theory, we have strong theory really only for the linear case. I think more theoretical work could be done here. It just hasn't been looked at very much. Okay, now I want to say this strange thing. I want to say on-policy methods typically perform better than off-policy methods, but they find worse policies. Okay, they perform better, but they find poorer policies. It's kind of contradictory, so I need to show an example to have this make sense to you. So this is my example. It's called cliff walking. We're just going to compare on-policy versus off-policy. And this is a picture of the world or the environment. So let's go through it step by step so we understand it. So it's a grid world type situation. We have a start state and a goal state. And we have these cells. So each cell, like this one, you would have the actions that move you in the 4 directions. So you would have an action that moves up, an action that moves right, an action that moves down, an action that moves left. So the usual actions. And if you do reach the goal, you get a reward of, well, actually, what is the reward? The reward is that bad things are no longer happening, because as you're traveling through this world, the rewards are all -1. So it's like you're getting hit on the head constantly, and then the only way to get the pain to stop is to reach the goal. And then, of course, you get transported back to the beginning and you start all over again. But it's an episodic problem, so to minimize the remaining punishment, remaining negative reward within the episode, you want to get to the goal as soon as possible. You actually want to minimize the number of steps to the goal. Okay, now the cliff, this world is a little bit different because we also have this thing called the cliff. And the cliff is a region that if you, say, step into it, you are sent immediately back to start, and you get a big negative reward. Okay? So it's much better to go through here and get not only 15 -1s or whatever it is, and then to fall off the cliff and get -100. Okay? Okay, so, and in particular, you might think of there being 2 paths. There's like the optimal path. The optimal path, you go just above the cliff and you walk along it and you get to the goal. But if you want to be safe, and we are going to want to be safe because we're going to be epsilon greedy. We're going to have epsilon greedy action selection, and that's going to mean you might step off the cliff. Okay, so you might want to do the safe thing. And that's really ends up being the difference between on-policy and off-policy. So here's the data, here's the results. I've put this up here so we can consult it, you can remember how it works. But this is the data. We're now going to, over episodes, over trips from start to goal, we're going to look at how much reward do you get. And they're all negative, right? Because you either get all these -1s through here, or you go here and you get -100. So everything is negative, so we want to get a lot of reward, so it's going to be high, but it'll just be not quite as negative. And we see that SARSA, the on-policy strategy, this is averaged over smooth, okay? But after a while, they both improve, but then SARSA gets more reward per episode than Q-learning does, okay? And the way to understand that is that SARSA learns to go up here. Remember, they're both epsilon greedy. They're both epsilon greedy, so they both have a 1/10th chance of picking an action at random. So Q-learning does learn the optimal path, right? Again, it's this thing. It knows the right thing to do, but it's not doing it. It's going to actually walk along the top, but then 1 chance in 10, it's going to explore, take a random action, and some of those will cause it to fall off the cliff. So it will actually do less reward on average. It'll get more, it'll fall off the cliff more often. SARSA goes all the way to the top and then creeps in here, tries to get to the goal. Now there's always a chance that it will explore. Say here, it could explore by going there, and then epsilon might come up again and it might explore again and go there, but it's much less likely than if you do what Q-learning does, which is walk the optimal path next to the edge. Okay? So now you know what I mean when I say Q-learning finds a better policy. It finds the optimal policy, but it performs less well. It doesn't get as much reward as what SARSA does. So that's, in a nutshell, the difference. But if you can understand that example, you will understand on-policy versus off-policy. Okay, let's have a demo. The point of this demo is I want to show you some things working. They're going to work with SARSA. We're going to use SARSA, actually SARSA lambda. And these are all using linear function approximation with what we might call coarse-coded features, linear features. The term that I like to use now is tile coding. In the old days, they called them CMAX. And the world just has this car trying to get up to the top of the hill. But the problem is its motor is too weak to directly counter gravity. In order to get to the top of the hill, it has to like back up and then take a running start to get to the top. Okay, so let me see if I can show this. Good. Okay, so on this side, we have the world. Let's just start it going. See here, I can actually reach the go button. And this little circle is the car. And the car has 3 actions. It can go forward, it can go backwards, or it can coast, which maybe isn't useful. Okay, and what are the state space? The state space has a position, right to left, and has a velocity. And so what we see up here is that state space, where this is the position, and this is the velocity. And as you might imagine if you were a physicist or a control engineer, at the beginning, you tend to rock back and forth. So that's a circle in state space, okay? And it's trying to get up to the top. So on this side, we have a representation of the value function. This is actually the value of being in each one of the states. So this 2-dimensional space projects onto this 2-dimensional space. The goal region is along this edge. And we can see if I press this button, it'll give us the action value function. So the action value function, it's basically, it's learned that being at the bottom is bad. I have to say what the rewards are. The rewards are like in the cliff world, it's -1 per step. So it's always being hit on the head, and the only way to end the penalty is to reach the goal. And so all these values are negative. And you've seen maybe 5 times now it's reached the goal, and so it's starting to get a useful value function. But I want to just kind of cheat and go ahead to save time. I should have the same thing from later on, and this should be it. Okay, this is the same thing. Now we're looking at episode 21, and the value function is much smoother and lower, in fact. But the behavior, so not only show you the behavior, it's going to be less random. It's going to pumping up nicely, efficiently, just enough times to reach the top. Okay, so that's a simple example of learning an optimal policy, for a control problem. And one thing that's nice about it is it's one of these non-holonomic control problems where you have to go away from the goal before you can go to the goal. Okay? The optimal policy involves first going away and then toward. So not only do you want to move in the wrong direction, but you actually move in the wrong velocity. You move to a negative velocity, whereas you really want to get to a high velocity going right. Okay, so that's mountain car. And as I said, that's just linear function approximation with coarse-coded features to give us that approximate action value function shown in the 3D graph. We have another demo. I think are going to go up in numbers of dimensions. This is called the acrobat, and it actually has 4 dimensions. You should think of it as if it's a person, an acrobat, hanging by its hands here. And this is here, he's bending at his waist. Okay? And so it can only apply force at the waist. And it's the same kind of thing. It can apply a torque clockwise, counterclockwise, or no torque. And that little arrow there is showing when it's applying the torque. And it's also the same in that the rewards are all -1 until you reach the goal. And the goal in this case is to get the feet, the very end tip point, above this line. That ends the episode. Now the other thing that I should say is how things are initialized, because it makes a big difference. And the reason all this behavior occurs, particularly on the first episode, it's because the initialization is what's called optimistic. It's initialized to, whoa. It's initialized to 0. Okay, that was the first episode. And we're going to jump ahead to the 40th episode. So I want to say that initializing to 0 is optimistic because all the real values are negative, and that causes it to explore. Whatever it does, it gets worse than what it expected because it was expecting 0, and so that causes it to keep doing new things. And actually on a problem like this, you don't need epsilon to be non-zero. This thing is done with epsilon equals 0. The other nice thing about this example, and this is the final behavior, is that it's rather a long policy. I think it's like 80 steps of pumping up energy into the acrobat in order to reach the top in the fewest numbers of steps. And this, which we're seeing here, is what it finally learns to do. Okay? That's acrobat. Good. Oh, I have another demo. Let's do some soccer. It's not full soccer. This is RoboCup soccer with the simulation league. I don't think it's used that much anymore, but it's really quite nice. And we're not going to do full soccer. We're going to do keep away, 2 versus 3. Okay, so let me just show you what happens in the behavior. Okay, we have I don't know. Let's look at these random players, because they're random players, so-called random players, but they're not actually doing that badly. The red guys are trying to keep the ball away from the blue takers, and the choices, the only choices are, should I keep the ball? No, so I'm looking at them. What are they doing? They never keep the ball. They always pass the ball right away. So the only choice is which of the two partners, teammates, to pass to. Okay, otherwise it's random. And still you do pretty well. Like if you just always pass to someone, you can do okay. You can do better if you make a hand-coded strategy. This is a hand-coded strategy that Peter Stone made, and they're a little bit more subtle and clever about when to pass and when to hold on to it. It's too bad this isn't running anymore. I want to run this one. This one is the strategy that says always just hold on to the ball. Never pass. Okay? You can still keep it for pretty long. So these are our competitors. Maybe the hand-coded is the strongest competitor. And we beat all the competitors. So this is the learn strategy. So the learn strategy decides when to pass, who to pass to, or whether to keep the ball. And we can show it does a little bit better playing this game. Okay, so that's another application. Now this application, I think it might be non-obvious what kind of features you would use of the state, because this is going to be done with linear function approximation. And I want to try to give you some insight into that, because this is the kind of thing you need to do all the time. Okay, so this is, the first thing we do is we take the whole of soccer and we turn it down to 13 numbers. Okay, and those 13 numbers are things like, well, how far am I from the ball? How far am I away from my teammates? And most importantly, how far am I from the takers? Right? Are they closing in on me? And we're also interested in these angles, the angle between the passing lane to my partner and the taker. Okay, if that's too small, he'll intercept it. Okay, and oh, this is important too. Like this is the center point of the ring, of the field, and you want to know how close you are to the center point. Like in particular, the guys you might pass to, are they right near the edge, or are they close to the middle? Okay, so we have these 13 numbers, 11 distances, 2 angles. So that's this step. We take the whole soccer position, we reduce it to 13 numbers, and then we have this technique that was used, for example, in mountain car and acrobat, in order to convert continuous numbers into giant feature vectors, giant binary feature vectors. So in this case, we have 40,000 components to our feature vector, but only a few of them are ones. All the rest are 0. And that means the computations we're going to do with it are really cheap. We're going to make a linear map from that feature vector to our actions. And so it's all going to be linear. And this part is just constructing features that are going to be used by the learning algorithm to get our action values. Okay, so now I want to return to the bad news. I think I've shown you enough things working that you're not going to be too annoyed at me if I delve further, and won't be too disappointed in reinforcement learning if I point out there's some things that we can't do and we're still trying to figure out. Okay, so the problem of instability. What causes it? Well, first, it turns out it has nothing to do with learning or random sampling. Because even if you just do dynamic programming, the classical solution method from the 60s, you do it for a known MDP, you're not learning, everything is known, you will have the same problem. You will have divergence with function approximation. So, it's one of the important facts of the world is that dynamic programming doesn't work with even linear function approximation. If it did, the world would be different, I think. What do they do in dynamic programming? They tend to just grid the world up and learn approximate values in each little grid cell. But the grid cells cannot overlap, and they can't have any sophisticated kind of multidimensional generalization. You can only have what's called state aggregation methods. You can't do powerful function approximation, not even linear function approximation with dynamic programming. So it really has nothing to do with learning, nothing to do with sampling. It also has nothing to do with, explore, exploit, nothing to do with greedification, nothing to do with control. Pure prediction, give me the policy, compute its value function. No changing policies. Still, you get the same problem. You get divergence. Policy evaluation alone, fixed policy, can diverge. In fact, the prominent counterexamples, Baird's counterexample, I don't think I'm going to show it to you. It's not really even that interesting to look at. But those examples are just given a fixed policy, a simple function approximator, a particular choice of features, and a particular choice of rewards and dynamics, and the parameters diverge to infinity. And that's for a simple linear approximator. We'll have instability. So it's nothing about complex nonlinearity. Okay, so what causes the problem if it's not these things? Well, it's what I call the deadly triad. These 3 things you can't do together. You can do any 2 of them, but you can't do all 3 of them together, or you have this problem, okay? The 3 things. One is function approximation. And of course, we have to do function approximation. We want to have a powerful, significantly generalizing kind of function approximation. And I'm thinking we want to do bootstrapping, which is this way of learning estimates from other value estimates. We will evaluate that. Do we really need to do that? But if you do function approximation, bootstrapping, and off-policy learning, then as we've seen, or as I've stated, we can have divergence with the weights actually running out to infinity. But any two of these, we're fine. So I've shown you all those positive results, and those are leaving out the third one, right? We did on-policy learning with SARSA instead of Q-learning, and then we had good convergence properties. So one thing we could do, one way to escape the deadly triad is to focus on policy learning. And that's, I've shown you positive cases, but I'm not fully happy with that because I want to do off-policy. I think off-policy learning is like magical. Like the whole idea that you can behave randomly and figure out the optimal thing is great. And one reason it's great, which might not have occurred to you yet, is this means you can learn about a million things in parallel because you don't have to do them. You could behave randomly. If you can learn randomly and learn the optimal way to get to that corner where the goal is, you could at the same time be figuring out the optimal way to get to the other corner. You could be at the same time figuring the optimal way to get to all kinds of places. You can learn in parallel. You can learn an infinite number of things in parallel from the same experience if you can do off-policy learning. If you can separate what you're learning about from how you're behaving. And so this is, for me, it's the big challenge of AI, is to get to a place where we can learn about many different policies without having to follow them all the time, right? You can only do one thing at a time. So if you're stuck with on-policy learning, you can only learn about one policy at a time. If you could do off-policy learning, you can learn about many things at once. Okay, but we've already dealt with number 3. Number 3, you could do on-policy learning and do well. But I've just said I'd really like to do off-policy learning, so maybe I can give up on number 2. Okay? Bootstrapping. Let's look at bootstrapping. Oh, I guess I have a little question. Why is dynamic programming off policy? Why is dynamic programming off policy? Dynamic programming doesn't have a policy, does it? In dynamic programming, you sweep through the state space and you update them all. Okay? But it turns out that sweeping through the state space is like a policy. It's analogous to what in a learning algorithm, it's, what places are we updating? Well, in a learning algorithm, we update wherever we are. But in dynamic programming, you just sweep over the whole state space, you update everywhere. And that might seem good, but it's actually like off policy because you're not updating according to where you would go if you were doing the optimal thing. And so the distribution of updates is not the same as what you would experience if you followed the target policy, and that makes it off policy. Okay, the third one, can we do without bootstrapping? Can we let that one go? Well, let's note some things. First of all, it's critical to the computational efficiency of dynamic programming. We estimate some states from other states, and that's really the basic logic of the principle of optimality. You only need to look one step ahead, and you use your estimate from the new state. It's really going to hurt us. What would be the alternative? The alternative would be to wait, to look at the full, all the rewards out to the end, rather than summarizing most of the future with your next estimate. And in a Monte Carlo, in a learning case, it would be doing Monte Carlo things, running all the way to the end, seeing all the rewards, rather than just the next one and then doing the update. So in the learning case, it's key to being efficient. Monte Carlo things are very high variance, and we can show that so key to the data efficiency of bootstrapping methods is that they're bootstrapping. The TD methods do that. So, but on the other hand, bootstrapping also introduces bias. And it's because you're influenced by your current estimates, and they could be wrong. And so that's going to hurt you. In the function approximation case, it's going to hurt you even asymptotically. So I'd like to go one step deeper and talk about that a little more finely. Okay, the problem, the way bootstrapping is not entirely good for learning methods, or it might seem really bad. So let's try to make it seem really bad. Okay, but first, I want to talk about lambda. Lambda is our bootstrapping parameter, which allows us to finally control the degree of bootstrapping. Okay, lambda equals 0 is going to be full bootstrapping. So far we've talked about full bootstrapping methods today. We've talked about sarsa, but really there's a sarsa lambda, which has a parameter lambda, which can vary from 0, which is the algorithm you've seen, all the way to lambda equals 1, which is not doing any bootstrapping and is like a Monte Carlo method. And so let's look at our loss and our performance as a function of lambda. And I think for this case, it's appropriate to look at the naive loss. The naive loss is we compare our approximate value function for states to the true value function. This is just for policy evaluation, a given policy pi. I'd like to learn its value, so I compare my estimates to the actual values, take the square, well, I'm missing a parenthesis there, take the square, and then the expectation. Okay? So, as I said, sarsa and lambda, or sarsa in general, will converge to a fixed point. And this is what we can say about the loss of that fixed point. Okay? This is how the loss, asymptotic loss of sarsa and lambda, and we're going to say it's less than something, so that's good. Okay? On this side, we have the best possible loss. So we maximize, or we minimize rather, over all possible parameters, say given our linear, this is all for a linear function approximator. So the mean square solution to this least squares problem, we find that theta and we use it. And so we're not going to do that well because that's the very best you could do. There's no way we can beat that, or we could equal it. But in general, we have this bias, and this bias causes us to need an expansion. Okay, so look at this expansion factor. If lambda is 0, like in Q-learning, and sarsa is 0, which is the ones I've shown you, then this is 1, this all goes away, and you just get 1 over 1 minus gamma. Gamma is near 1, so this is small, and this is a big expansion. Okay, maybe we can only do, if gamma is 0.9, we will, the error of our algorithm will only be guaranteed to be within 10 times the error of the best possible theta. Okay? And some other things to notice. Well, what if the loss is 0? There's an exact solution. If there's an exact solution, the loss is 0, then this bound is quite strong, right? Because this is 0, so we will also be 0. Okay, but if lambda is 0 and this is non-zero, we have an expansion factor that's significant. Unless, if you're staring at this, unless you're saying, well, what if lambda is 1? Lambda is 1, then I have 1 over gamma over 1 minus gamma, and it's 1, and I'm just as good as the best possible. So you might, this analysis tends to suggest that, at least asymptotically, lambda equal 1 is the best, which means no bootstrapping, which would be great, because I can escape the deadly triad and have good convergence properties. Okay? But sadly, it's not true. I mean, the math is true. That's a theorem. Tsitsiklis and Van Roy. Tsitsiklis and Van Roy. This is our most important result about the convergence bound. It's absolutely true, but somehow it's not what we want. Okay? Because if we actually run things empirically, and we just measure how well we do, and that's what lambda equals 1 is terrible. Okay? So let me take a couple minutes and explain this graph. This is 4 different problems, and there are, obviously there are many more problems, and these are I believe representative, but you could do more. Someone perhaps should do all the Atari games with every different value of lambda and find out how well it does. So in all these cases, the good performance is low. Okay, so here's mountain car, and here we're varying lambda. I don't know if you can read the x-axis, but it's varying lambda from 0, in other words, pure bootstrapping, to 1, no bootstrapping. So remember, our theory says that lambda equals 1, the rightmost data point should be the best. But remember, lower is better. Okay, so I've circled in red all these cases with no bootstrapping, and they're the worst. They're the worst. And this one is off the screen. Off the graph. If I run lambda equals 1, I can't ever converge. I can't ever get good performance out of it. Now, all these measures are not asymptotic measures. Okay, so it's not violating the theorem. These are all how well you did after a certain number of episodes. After a certain limited amount of experience, what's the quality of the solution? Okay, and so it's perfectly possible that if I really ran longer with lambda equals 1, I would be the best. Okay, but in practice, that seems to be a very long time, and you just lose if you try to use lambda equals 1 all the time. Okay. Now, you might also notice, say here, that lambda equals 0 is not the best either. No pure bootstrapping is not the best in all cases. Typically, it's kind of a U-shaped curve. So the best thing is, we want to do some bootstrapping, but not pure bootstrapping. But we don't. Neither do we want to do pure Monte Carlo or no bootstrapping. We want to be somewhere in the middle, and that would be problem dependent. Okay, so I think I'm done with my analysis of bootstrapping. I want to conclude that we don't really want to give up the bootstrapping. It's important not just computationally, but for getting a good behavior in a reasonable amount of time. Okay, so let's talk, as I'm winding down, about other ways to survive the deadly triad. The deadly triad, remember, it's function approximation, bootstrapping, off-policy learning. So we've been aware of this problem for a long time. How long has it been? It's maybe 15 or 20 years now. And so people have tried various things and succeeded to various degrees in surviving the triad. And so what are some of the things? Let's start with the trivial ones. Well, first you can just use high lambda. Okay? We widely believe, I think there's some theoretical results as well, that the higher lambda is, the less susceptible you are, the less likely you are to run into the instability. You can also win by using good features, like if you have table lookup, then you can't diverge. And the general feeling is if you have features that are better, more Markov, tell you more about the state, then you're less likely to run into the problem. Okay, but these are I'm just starting. Okay, these are just sort of practical ones. This is also somewhat practical. Recent results suggest that using replay, which means storing your experiences and playing them over again, that can help. Or stabilizing the target policy. So remember, the derivative is not taking into account the effect on the targets. And the idea is to just freeze that process, hold it stable, force it to be stable, and only update the first part that you're only updating anyway. So I like this algorithm of double Q learning, which Otto van Hasselt proposed a while back. And so I think there are some good ideas here, potentially good ideas, but it's really too soon to know whether these things are helping. I mean, they will show you results where they help, but it could be due to lots of other things, or they could be other things that will work just as well. Another thing you can do, maybe it's like cheating, is to use least squares methods. Those will all work really well. They don't suffer this problem, but they suffer the computational cost of a least squares method. Their computation is the square of the number of parameters. But that's another way to proceed. If you don't have that many features, you can do that and get good results. Now some newer things. One strategy is we're not doing the real gradient descent. So let's stop that. Let's do real gradient descent. And can we do, now it's not, gradient descent is not, like always good. It's not like it's moral or appropriate to do gradient descent. You gain no points in heaven for gradient descent. There are other things you could do that also can have good convergence properties. You don't have to say, oh, it's not gradient descent, it's wrong. Gradient descent is actually a very weak strategy for making something converge, but it's also very robust. I don't deny it. But we shouldn't just say these algorithms are semi-gradient, so they're bad. It means I'm just trying to say they're almost gradients, but they're not. It's a good way to think about them as gradients, but they're not. Oh, the word semi-gradient, by the way, is a word I made up just for this talk, okay? What else should we call them? In the first edition of the textbook, I think I just called them gradient-based Q learning or something like that. And then I almost called them pseudo-gradient, you know, but pseudo-gradient means false gradient, and it really sounds like you're doing a bad thing. And I don't want to apologize for doing this thing which is not a gradient. It could be a good thing, and this is generally what we observe, that the TD methods will converge faster than things that try to do gradients. Okay, like the residual gradient algorithm mentioned here is doing true gradient descent, but it goes very slowly, and moreover, it optimizes something that's we don't really want to achieve. And so I'm just going to say we don't really want to pursue that, but there are other methods, these new methods, gradient, what do we call them? Gradient TD methods and proximal gradient TD methods by Hamid Mai and others out of my lab, and Mahadavan and others out of the UMass lab. These are trying to do real gradient descent, and it's quite a challenging, interesting theoretical problem. And I think they are good attempts. They still have problems with variance, but we're just figuring out if these are the best thing. So you could try those, or you could try, there's an even newer thing that some of us in Alberta have proposed called emphatic TD. And I'm just going to say the tiny amount, which is that these also will converge. They survive the deadly triad with convergence. They're stable. And they're using something more like the early theorems generalized to handle the off-policy case. Okay, so I'm kind of done, but I have some closing remarks. And that's really along the lines of what I said at the very beginning, which is that, you know, there's all the things I wanted to tell you about, but there isn't time. And so I got a sort of grab bag of additional things I wanted to say. And so this may anticipate some of your questions. Well, first, just notice, this is the closing remarks, is these dimensions that we've really tried to break the overall problem of AI and interacting with the world and optimal behavior into various dimensions. So the first dimension, the most important, is always problems versus methods. So among the problem dimensions, we have prediction versus control. These are two different problems, and we've utilized that to make more precise statements today. Another problem dimension is MDPs versus bandits. I've only talked about MDPs, but there's a huge reinforcement learning literature on just bandits. So these are cases where you only have one state, and you still have to do trial and error to find the best action from that one state. But you don't have to worry about being transported to a different state, taking that into account. It's not sequential in the way the full MDP is. So bandits, this is a problem dimension. And all these other ones are algorithm dimensions, solution dimensions. So tabular versus function approximation, as we've talked about today, on policy versus off policy, as we've talked about today. We've talked a little bit about the bootstrapping dimension, like I showed that graph where he varied the degree of bootstrapping. And I've talked how we can unify it with a lambda parameter. A couple other dimensions we haven't talked about, where we can also use function approximations. We can make model-based reinforcement learning, and we can also make policy-based reinforcement learning. So I'll talk a little bit. I have a couple slides on each one of those so that they're included. But sort of the thing I want to say, I don't know if I can claim that I've shown it to you in any sense, but this whole space of methods, they're not just every corner of this space is different. In many cases, we can unify things like we do with eligibility traces. And we can even unify like model-based and model-free. All these versuses can be turned into ands. So we could do model-based and model-free. You can do value-based and policy-based. You could do, well, when you have eligibility traces, variable lambda, intermediate lambda, you're really doing both of these. It's sliding between them. Okay. So this is a picture of how we usually think about policy-based methods. So the terminology is a little confused. They used to be called actor-critic methods. Now we tend to call them policy gradient methods because it sounds like we know something more sophisticated. Actually, I guess I introduced both of these words, so I'm at fault. So anyway, we have our environment, and then on this side, in the agent, we have two things. Instead of just the one action value function, we have a value function. Usually it's a state value function. But we also have a separate box that is just for the policy, and it has its own set of parameters. And so that, like, if this part dies, the policy could still live on and make actions, and you would still have an agent. Okay, the policy is on its own, and that can be good in lots of ways. Actually, the next slide reminds me of those. But let me just say, then we will adjust those parameters by gradient descent. Some kind of gradient, actually it's gradient ascent, because we're going to go up in performance rather than down in error. And some people get really excited about policy gradient methods and how they don't need to use a value function, and because then you don't have to worry about all the problems we worried about of divergence and so forth. So you can do this without a value function at all, and you just get high variance. So you want to have a state value function, and as long as it's learning in a non-policy way, you have good convergence properties. Okay, so why would we ever want to make a policy approximation rather than value function approximation? We love value function approximation. I'm just showing you all how to do it, and we have our theorems about it and everything. But lots of times you really would rather do a policy. For one reason, the policy might just be simpler. You know, these are two structures, the value function, the policy. They could be, one could be crinkly, and the other one could be smooth, and it could go either way. So sometimes the policy is better. Another issue is that the policy you're looking for might be a stochastic policy. So in lots of card games, like in poker, or in fact in POMDPs, in case where you have hidden state, partially observable Markov decision processes, it's known that the optimal policy is a stochastic policy. So you have to, like, let's say in poker, you have to bluff, but you have to bluff, like, you know, 23% of the time. You can't just always bluff or always or not bluff. You have to have a probability. And think about action value functions. We pick our actions by greedifying. So, you know, there's one action that has the highest action value, and we do it most of the time. We only explore occasionally. So it's really hard to learn a stochastic policy when you're using an action value method. Not impossible, but it's not a natural thing to do. It's also this problem I alluded to earlier with action value methods is that one action value exceeds another one just by a little bit, your policy could change radically, and that makes the analysis more difficult. And so with policy approximation, we can get smoother changes. Finally, you can also avoid the max, considering all possible actions to find the best, if you can just store the policy, and if you have lots of actions, that can become important. And then for relating to biology and neuroscience, this also seems to be preferred to approximate the policies. Okay, this is just a slide where I tried to make lots of people mad at me. I'm going to say that we should never be using gamma. We should never be discounting. And I think I'm not really prepared to argue for it too much, but I just want to get on the record. We're doing this, we should stop it. We should stop because it breaks the definition of an optimal policy once we're doing approximations, because the optimal policy is no longer representable, and so there's no way to rank the remaining policies, because and when you're doing approximations, one policy may be good over there, and a different policy good over here, and you can't just use discounting the way you can in the tabular case. So what I think we should be doing, we should be doing average reward per step methods, like reward rate methods. And that's also well understood, but it's done much less. We should probably be doing it much more. All those guys at DeepMind that are doing Atari should not be using discounting. They should be doing average reward, it seems to me. Okay, now I said I was going to say something about model-based reinforcement learning. So the idea is we're doing approximation, so let's learn an approximate model of the world. You may not remember, the world is described by transition probabilities, so we're just going to learn something that approximates those. And then we will use this model to generate, well, this is one way that I find appealing. It's not the only way to do model-based reinforcement learning, but you could use it just to generate trajectories and then apply your original methods to the simulated imaginary trajectories, as if they had happened. You know, just do the usual thing on the imagined experience. And this will actually give you planning and model-based stuff, and you can mix it with direct reinforcement learning. And I have a quick demo. Okay, so this is our usual kind of grid world. This is a CAN demo. And we're learning a model now, and because we're learning a model, when we first stumble upon the goal, you saw it, just got to the goal. Now all these are being updated quickly. Even though you're not here, these are being updated because it's using the model to imagine being in those places. And these are places it never visited, so the model doesn't know what the transitions do there. It doesn't know what they do here. But because we learned a model, then as soon as we discovered the goal, as soon as we included the goal in the model, we were very quickly able to recompute a good policy and a good value function. So one way to show that is to change the goal. So here, someone's reaching in and moving the goal to a new place, and our agent will go where it used to be, thinking it's good. All that green means it thinks there are high action values. There are high action values in that area. There are high estimates. And so when it finally stumbles on the goal, then it will plot the path to it very quickly. So for example, these things are being figured out even though the agent is not in those places. Oh, I'm pointing. These things are being figured out even though the agent is not in those places. So let me do that one more clear time. So here it's going where it used to be. Why are these values going down? They're going down because of gamma. It's going back and forth between states that all have about the same value, but it's disappointed because of gamma. Because of I'm using discounting, even though I said we never should. But this is a tabular case. It's not function approximation, so it's OK. Actually, it's episodic. So as long as it's episodic, you're OK as well. OK, so eventually it will wander in here and discover the goal, and then you'll see very quickly, even though it isn't in these places, it's figuring out what the right action is to do in all of them. OK? Good. That's what you can do with model-based. But that's just a grid world. You can also do model-based on real-world problems. So the guys at Stanford, Andrew Ng, did model-based with helicopter autopilots. Let me just show you a clip from that. So this thing is flying upside down, and it can just do arbitrary acrobatic maneuvers. It's going to flip. So this was done by learning a model of the world and then running enormous numbers of simulations, like it crashed the helicopter so many times in simulation. And thus we were able to use a trial and error learning method on a problem that it would be dangerous to really do experimental things. OK. Must be almost done. But I never talked about eligibility traces except in very general terms, so let me continue talking a few more things, because I really like them. I think they're elegant, and I've done so much work on them, so I want to tell you a little bit about them. I guess I'm disappointed you're going to leave this room and you'll never have seen an actual algorithm using eligibility traces, but you can't have everything. So I think the key, we're getting a deeper understanding in recent years about why we have them. And the reason we have them looks like it's mostly about computational complexity. You would want to use eligibility traces, it turns out, even if you were not doing bootstrapping, even if you're not doing control, it turns out even if you were not doing reinforcement learning, I guess if you're not doing either bootstrapping or control, you're probably not doing reinforcement learning. So yeah, I think they're actually important in just for certain kinds of prediction, long-term prediction learning that are supervised. They're also, in reinforcement learning, we have this time step. And it may seem harmless to have discrete time, but we are assuming a little bit stronger than that. We're assuming that the world's causal dynamics work at our time step. And if you want to move beyond that into real continuous time systems, you need to use something like eligibility traces. And as I've sort of mentioned, it's one of the most algorithmically intense topics. This is where we really get into importance sampling, and where we really worry about keeping the variance down. OK, I wanted to mention temporal abstraction. Function approximation abstracts over state, but we also need to abstract over time, which means think not just about actions like right, left, up, and down, but like an action like going to the talk or going to the conference or taking a job offer or picking up an object. And these are all things that take extended time. And so there are some theories that try to deal with this in interesting ways. And, but it's a complex problem with great depth. So in conclusion, reinforcement learning is a big topic, long history. I think an elegant theoretical core. Certainly we have novel algorithms and open problems. And once we get into things like temporal abstraction, it's really appropriate to call them vast unexplored territories. So we can view the reinforcement learning problem as like all of the AI problem or the problem of mind in a microcosm. It involves planning and acting and learning, perception, modeling the world, even knowledge of the world. And yet, even so, it can be reduced to these small steps on which we can make progress. It also fits into this megatrend, what I call the megatrend in AI, in which certainly what we see now in deep learning and in so many people coming to NIPS, is that we're turning more and more of the work over to the machine. And reinforcement learning, since it requires less of the trainer, really fits in well to this big trend. And finally, I want to remind you of these three words. I always try to summarize the idea in as small a way as I can, because I think all good ideas are simple if you look at them the right way. And so the idea of reinforcement learning is to be more realistic about the problem facing a learner interacting with the world. And in that sense, it's more ambitious. And yet at the same time, I hope that we're being more pragmatic. We are being pragmatic in our picking the problems to work on. Thank you very much. I'll be happy to take a few questions if anyone wants to go to the microphones. The microphone, there's one microphone. There's two microphones. I have no idea where they are.
They're right on the aisles.
They're in the aisles.
Hi. Thanks for the talk. You talked about model-based and model-free and said that we can do this, and I was just wondering what you had in mind there, or if you could talk about it a bit.
So actually, the demo that I showed of the grid world was doing exactly that. It was both learning from the real experience and shoving those into an improved action value function, and at the same time, it was learning a model and then using the model to also improve the action value function. So the action value function was serving as the final common path of both the direct learning and the model-based updates. It's really kinds of interesting ways. There are multiple ways to intermix them. In some sense, replay is a way as well. You store the old example. The storage of all the old examples is a kind of model of what might happen. And when you replay it, you're also combining, you can both replay experience and do direct experience. Lots of natural ways to combine them. Thank you for that question.
Here, so it's nice to hear you talk about three deadly triad. Basically, 3 are bad, 2 are good. Are they empirical observation, or do they have theory underlying these 2 statements?
I guess, since it's a negative statement, it says we've never found a way to put these 3 things together. Well, what we have, actually, the new methods do bring them together. Yeah, so it's not a theoretical statement at all.
But how about 2? Having 2 are okay, are good. Is that theoretical? Any proof on those?
Well, let's see. If we leave out off policy, we have the results that I showed you. If you leave out function approximation, table lookup, yes, that's a theory. We know that all works. And the third one is bootstrapping. If you leave out bootstrapping, then you're in some sense in the usual supervised learning situation where you have regular outcomes. And yeah, you're right. So for the positive result that any 2 are okay, that's theory.
Oh, yeah.
Yeah.
Okay, thank you.
Hi, I'm sure you've read the DeepMind paper for training the algorithms to play Atari games.
Yes.
In that paper, they use a trick called experience replay.
Yes.
So I was thinking, is that some form of model planning, or is it an approximation? So how does it relate?
So the classic replay is you store the experiences, and this could be just the 4 tuples, or little snippets of experience, like state, action, next state, and reward. And then you put them into a memory, and then you play them over again. Okay? You pretend they had occurred and learn from them a second time, and maybe multiple times. And so this is the idea of replay. And yeah, it's kind of like a model base if you think of the memory as like a model, but it's a particular kind of model. And They claim that that's really important to surviving the triad, to getting stability. But I think other people have found that they can get stability in other ways without doing that. So I think that's an open question. Thank you.
Thanks.
Sorry, I might have missed your first part of the talk, but I was wondering, do you see a lot of strong similarities between reinforcement learning and deep learning? Because, for example, the forward-backward could be treated as a TD sort of algorithm.
So I like to think that they are orthogonal ideas. So deep learning is about function approximation, and reinforcement learning is a consumer of function approximation algorithms. So we see, like with the Atari result, is exactly taking classic reinforcement learning algorithms like variations of Q-learning and combining it with a sophisticated function approximator, the deep learning. And so they're orthogonal. They come together well.
Sorry, I need to clarify a little bit. I was imagining each layer to be a state, and in that way.
Yeah, so you could try to think of something, I don't know. There's back propagation, which things propagate back, and there's bootstrapping, where things propagate back from the goal, and these kind of have a similar feel to them. But as far as my own experience, that line of thought is just a mistake. You should avoid that. I don't see that. I think that's just a confusing, superficial similarity, and it's not a deep similarity. But I could be wrong.
Thank you.
Thank you.
Hi, thank you for the talk. I had a question. In the frame of reinforcement learning, we typically think of the reward coming from the environment. But in the frame of kind of a science of mind and brains, it seems that our rewards are encoded neurally, presumably maybe programmed by the genes. And so in some sense, those were learned maybe through a evolutionary algorithm. What's your perspective on that in the large, and also kind of learning rewards more practically in the reinforcement learning setting?
Well, first, you're absolutely right in the sense that rewards they're computed inside our heads, and so they're part of the organism. Okay, so I would just say that the organism is not the boundary of the agent. So the agent maybe is your policy choice. It's inside your body. So, for example, your arms are definitely part of the environment. They're not part of the agent. You have to learn how to control your limbs to achieve things. So it's all okay if you just say, well, the agent-environment boundary is not the organism-environment boundary. Okay. So now, but then the deeper question is, where do the rewards come from? And one part of me wants to just say, I'm not going to address that question, because as an AI agent or as a goal-seeking agent, ultimately the goals have to be arbitrary. The nature of a goal, the nature of a goal-seeking system is it can achieve different goals. And so, the choice of the reward function is really important for us as creators of AI systems, but for the design of an AI system, I see it as less important. Okay, and then this leads me to not worry about how we should give rewards to our agents. That's sort of an outside thing. But it's now 2015, and I realize I have to be a little bit more conscious of societal effects and things like that. And so I don't know. How am I more conscious now? It's still a separate thing. It's not part of the technology of optimizing whatever reward you have. So I see it as an important, separate question. Let me stop there.
All right, thanks very much.
Markov state is supposed to depend on the state, Markov's processes. But some of the articles that I have read on marketing and on driving gets around this by incorporating the history as a part of the state. Is it a valid approach theoretically, or is it a trick?
Oh no, it's the only way. If you want to incorporate more of the state, you have to incorporate the history. And we need sophisticated ways of doing that. Those sophisticated ways, when we find them, will be exactly that, incorporating more of the history in a compact, clever ways into the state estimate at each point in time. Thank you.
Thank you.
Thank you very much for a very informative tutorial. I enjoyed it, and especially the slide where gamma, the decay parameter, should go away. And here is my question. So, of course, I understand that, let's say, average reward per step is probably much more accurate metric, but the Bellman equations crucially depend on that possibility to aggregate all the future dynamics into this one term, and it's based upon this nice structure with that decaying parameter raised to the power n. So if you get rid of this gamma, what will replace the Bellman equations?
It's going to be okay. There are Bellman equations for average reward. We really don't need gamma in order to have Bellman equations. In order to have TD errors, all of the algorithms carry through without gamma. We're just not used to doing it, and so we haven't done it. Like if you go read the books on Markov decision processes, like the Puderman book, there'll be huge sections that are all about, there's the discounted case, and then there's the average reward case. It really is our fault, our laziness, that we have not gone ahead and gotten rid of gamma.
Thank you.
Thank you.
Hi. How solid is, how robust is this framework to structural changes in the underlying causal structure you're trying to model?
So, first of all, one way it's extremely robust is that it doesn't model the process. Reinforcement, direct reinforcement doesn't model the world. It just finds a good policy. Now, another part of the question is, what if the world changes? What if it's non-stationary? We absolutely have to be able to handle non-stationarity. Of course, the convergence results are not about handling non-stationary, but the algorithms will usually handle it perfectly well. Like I could show you another demo where we do the model-based reinforcement learning, and now the model changes. Well, like I did show you one, I guess I picked up the goal and moved it to another place, and it just started adapting to the new place, kind of tracking the latest model. So I would like to say that this is one way where reinforcement learning is a big win, because we're not giving in strong assumptions about the generator of the data. We have an arbitrary data, and we're just seeing it. It's not very modeled. It's not based on a strong generative model of the world the way much of the work in our field is.
If I may add to that briefly, so if there's a delay in the recognition of the feedback, does that complicate matters incrementally to what you just described?
So I think you mean, well, if the world changes, if I move the goal to a new place, it takes it a while.
No, what I mean is if the world changes, but you won't get feedback if there's a big difference between your action and the received feedback, does that impede the likelihood of actually reaching a good solution?
So I think you saw that, right? It went where the goal used to be, wasted lots of time confirming that, and then, so it does delay. It does increase. It's not a big problem.
Thank you.
Thank you.
So I have a question about deadly triad that you mentioned. So I'm assuming that the deadly triad.
About which?
The deadly triad.
Yes.
So you said if we have all of them on, like if we use all of them together, then it's not guaranteed to converge at all. But I mean, it's also true in like other, if you take analogy, it's also true in say non-convex problems, right? And people tried it anyway, and people came up with tricks, and they made say deep neural networks work. So do you think that like the future could be like just trying out and finding out new tricks and making it work, or like should we really pursue and like more theoretical?
It's absolutely true that Q-learning with function approximation, it's got the whole deadly triad, and it will almost always work. It will almost always work. Maybe in some sense it could be fine. But I'm thinking it's a clue. It's a hint that something is wrong. And rather than ignoring this, we should pay attention to it and figure it out. It's a hint or a clue that our theoretical notions are incomplete and we're missing something. And so the fact that if the situation comes up just the wrong way, the weights will go to infinity. I think that's a clue or a hint that other cases that maybe are not quite so bad are still doing something that's not the right motion. Okay, and so I think it's going to be hurting us, and we need to figure it out. But it's really perfectly true. And so many experiments have been done with Q-learning, with function approximation, and I don't know if anyone's reported in the literature divergence in a problem that they actually cared about. I'll say no, and if anyone knows one, let me know. I think it's never been, here's a problem I care about, I applied the deadly triad and it failed. What we have is counterexamples, constructed counterexamples to make them fail. Yeah. Thank you.
Could you give us some intuition why on policy would be more stable than off policy? Because for me, for instance, in Q-learning, you're taking the max, so you're kind of less dependent on bootstrapping.
Okay, so there actually is a very good, a fairly easy explanation. So when you're on policy, you go from one state to another state, and you bootstrap. You use the new one to improve the first one, and then you always have to go on from that new one to another new one and bootstrap to it. But with off policy, that doesn't have to happen. You might go from one state to another, you use the second one as a target, and then you never update the target. Because you, maybe at that next state you don't do the max action, and therefore you will not update that action value. So it kind of, there's the off policy case, you know, everything that you use to update something else also has to be updated an equal number of times. You go into a state, you have to go out of it. But in the off policy case, when you go out of it, you don't have to update the value of that. It's really a state action pair. Yeah, so that really is it. It's the fact of trajectories. That when you go into a state, you have to go out of it. So it has to play both the in role and the out role. Whereas in the off policy case, you might only play one of those two roles, and thus you have things that are never updated or not updated enough, and with generalization, it can make things explode. Thank you.
Thanks.
Yeah, so you talked about the linear case, but I was wondering if we do want to start working on, nonlinear function approximation, where should we start?
Well, I think there is a natural place to start, which is semi-linear, by which I mean a single linear unit, and then you have a nonlinearity, a sigmoid function. Okay, we really should do the case of that case, linear followed by sigmoid. I don't think we have theory completed for that. It might be very different. That's where we should start, and then continue.
When we do policy search, how can we control the complexity of the policy in order to obtain good generalization properties of the algorithm?
I guess we don't have an answer to that question. I mean, that's like the question of how do you pick the structure of your function approximator. There's the parallel question of how do you pick the structure of your policy. I mean, we have some standard ways, some standard structures, but they are just standard. We don't really know, we like to say in policy gradient land that you can pick any parameterized structure to be the policy. So we have standard ones for, like if you have a multinomial choice and then you want to have exponential form. And we have standard ones for the Gaussian, like if you want a real valued continuous action, you can pick it from a Gaussian distribution. But the choice of what's a good structure that will generalize well is like the question of what's a good function approximator that will generalize well. Still unknown, perhaps.
And what about the VC dimension? Could you try to control the complexity of the policy by perhaps trying to look at the VC dimension that it induces over the action spaces?
Let me just say yes. Yeah, I think in that might be a direction that would get you a finite time convergence analysis. It could be quite interesting.
Thanks.
Thank you.
Yeah, early on in the talk, you mentioned a contrived counterexample. I was just curious what it was.
Oh, well, this is in Bertsekis and Tsitsiklis paper. I think it's the same one that proves the bound, and it's kind of a spiral. It's contrived. I don't know, but it's in that paper, and Yeah, there's this kind of spiral boundary. And if you do it just right, it gets bigger and bigger. That's the best I can do.
Yeah, thank you.
Hi there. So you had talked a lot about different exploitation policies and had mentioned a little bit the explore-exploit dilemma. I'm wondering how much the deadly triad and maybe some of the other problems you had brought up might be tied to the exploration policy itself. Yeah, sorry about the mismatch in tone. That was my question.
Yeah, so I said, and I think it's true, that it has nothing to do, and provably nothing to do, well, provably. Well, actually, I hate the word provably. I think it's something should be either proven or not proven. It should not be capable of being proved. If you're capable of being proved, then you're proved. Anyway, sorry about that. Yeah, so the reason we know the explore-exploit trade-off is not part of it is because it happens even for policy evaluation. So the given policy, and I'll give you an infinite amount of data, there's no need to explore. We will still diverge.
Okay, thank you.
So when we try to apply reinforced learning, so the first step we notice is there you have to define state and value function. So, do you think is there some methods? And also in your tutorial, I don't remember you talk about dealing with the state definition. So is there a way, for example, to not start with definition of state, but going direct with a continuous state, or are there good methods?
So I think we're doing this already in the right way, which is that in our mathematics, we talk about the state value or the state action value. But in our algorithms, we never deal with distinct states or states that are identified in any way. We just have this function. So Q hat nominally takes in a state, but really it takes in whatever information you have about the state. So you could take in, like you might have a robot, and the robot can only sense certain events. You can't sense the whole state, and yet we will still say that the say state value function is a function of the state, because it's the function that first takes the state and converts it into sensor readings, and then takes the sensor readings into a number. Okay, so that's still a function of state. It's not in any way cheating to write state value functions or state action value functions in here. Thank you.
Thank you.
Hi, thanks. So to apply this to cognitive science, where the reward function, say, of a human is very complex and varying, would it ever be constructive to utilize a more structured reward in addition to a scalar reward function?
Well, to model humans and animals, I would want to first proceed with the naive hypothesis, or the default hypothesis. What do they call it? The null hypothesis, that it's the same, that people have a single reward function, it doesn't change, and that everything else is done by value functions and by function approximation. I think that null hypothesis has not been disproved, and I'm rooting for it, I guess, also.
Thank you.
Thank you. Thank you all.
All right. Yeah, thank you so much.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.